So, homework number 12 is due on Wednesday, the same day as our test, because part of that homework is included on the test. The test is going to cover what topics? First one is liquid pressure, right? Liquid pressure. And then it's going to cover the entire chapter 6, which is on trusses and frames. Trusses, frames, and machines. And then the first part of chapter 7, only the part on finding V and P, V, and M at a specified point. Okay. Now you need to know that what's P is the axial force, V is the shear force, and M is the bending moment. That's from this new homework. That's due. Okay. Any questions on the sample test or the homework that's due? Let's look at the homework. Let's make sure it's really included on the test. Let's see. Oops. According to name. So problem set number 12. So let's see. So that's definitely included number 4, number 15, number 29. Okay. So the test will only cover up to problem number 15. The maximum absolute values of the shear and bending moment diagram. So maybe we can so let's see, what would I do here? So maybe we can say that I can move the due date to Monday. Let's go back. So, Max, your homework's here somewhere. Here. Okay, hold on a second. So, huh? Oh, I can do that. So, but up to number 15 is included on the test. Okay, so let's stop sharing. Pause sharing. Okay, so let's move this to Monday, so you can focus on studying on the test. This will be the 29th, but the test will cover up to problem 7.15. Okay. So I need to share my desktop again. Oops. Oh, I'm sharing. I was sharing. So what do I do now? So I was sharing before. I think I'm still sharing. Am I sharing now? Yellows. Then are you still logged in? Can someone log in just to make sure that I'm sharing? Can you make sure that I'm sharing? Because I shared and I shared and I shared and I shared. I don't know. Okay. So you want to look at, say, the first problem on here? Oh, no, this is not how I do it. I use PDF annotator. Okay. Open. Problem set 12. So let's look at the first problem. So we are given this bent bar when alpha is 0. So this force here is really what? Open. So I'm not sharing, it looks like. What? Huh. I knew there was something. Stop sharing. Okay. Because it's the yellow thing is on though. Okay, let's do application sharing. Stop sharing. Let's do stop sharing. Okay, that's gone. I'm sharing again. Thank you for checking. Okay. I thought there was something going on. Okay. You don't want it to not be. It's sharing now, right? Thank you. Okay. Okay. Determine the internal forces at point J when alpha equals 0. If alpha is 0, this, how much is that? 1.4 kilonewton force will just be to the left. Okay. And we're interested in the what's this? The internal forces and bending moment. So this is the P, the V, and the M at point J. Before we do that, we're going to need to find the reactions. So first step is find the reactions at the supports at D and E and A. Okay. I'm going to be lazy and put the reactions right on this drawing. I'm going to, since D is a pin, I'm going to have dy in general and a dx. And A is a roller, and it looks like it can roll up and down that wall there. So it's going to be, I'm going to assume it to be to the left, AX only. Okay? So I'm going to sum moments about point D equals 0. I'm going to have a 1.4 times, what's the perpendicular distance? Looks like it's 0.2 minus AX times the perpendicular distance of, what's that? 0.2 plus 0.175, 0.375 is equal to 0. I'm going to get an AX that is, what? What's our AX? Our AX is, who has the calculator? It's going to be 1.4 times 0.2 divided by 0.375. Okay? And then I'm going to sum forces Y. It looks like dy will be 0 because all the other forces are horizontal. And then I'm going to sum forces X. I will get minus 1.4 to the left minus AX. What's AX? What's the calculator? Can you do that? 375. That's like half of, no, not really. What? Yeah, the AX is wrong. This is 175. Is that what you're saying? I'm showing once about point D, so this one is 175. Okay. But still, I need someone to calculate that. 1.6. Okay, so this is going to be minus 1.4 minus 1.6 plus dx. It looks like dx is going to be 3.0 kilonewtons. So I have all the reactions now at all the supports. Now I'm going to take a cutting section through J. I'm going to cut. And when I cut, I have an option to look at the left free body diagram or look at the right free body diagram. I think the right one looks slightly simpler. It shouldn't make a difference in terms of your answers. Your answers should be correct if you do it correctly, regardless of we take the left or the right. If I take the right part, okay, the forces I will see are, of course, the dx, right, would be how much? 30. The dy is 0. right? Which means that in general, what forces do you develop at point J when you cut it? You develop the P, the V, and the M. What direction of P should I assume, left or right? This is the P. Should I assume left or right? Why left? Okay, for P, for the axial force, we always assume positive to be tensile. The V, which is this one here, should be up or down? It should be up because our sign convention for positive V is making it rotate clockwise, and sign convention for M is making it smile. So that's our M. So we just sum forces along X equals 0. So we get a P that is 30 kilonewtons and positive, therefore it's tensile. We sum forces along Y equals 0. We get a V that is 0 because there's no other vertical force. And we sum moments about point J equals 0. What do we get? I'm going to get a 30 coming from dx multiplied by, what's that perpendicular distance? Is that 0.175? 0.175. Okay? That's the only force with the moment about point J, because both P and V are passing through point J, so minus M equals 0, therefore I find M. Okay? So the topic, I wanted to include this topic on this upcoming test because this is actually an easy topic. You know, just finding reactions in cut, show the P, the V, and the M, and just find those three. And that will generally help you on your test score. Okay? I do not want to include the later part of homework 12, which is shear and bending moment diagram. Right? Although we've finished it, we've done shear and bending moment diagram. So we still need maybe some more examples and practice, but we've finished the topic. I don't want to include that on the test because that one tends to take a little bit more time for you to develop the skill to do it efficiently. Huh? So this one here is finding the shear force and the axial force and the bending moment at a specific point. Take note here, I specified find it at point J. Okay? See, so you cut it at point J. But in the shear and bending moment diagram, you have to cut it at all different range of values of X, like we did last time, and then you graph how it changes as a function of position. Okay? That part is not included on this test. It will be included on the next test. Okay? Is that clear? So I'm going to move the due date for the homework, but you make sure that you do the first two problems here because these are not shear and bending moment problems and they're included on the test. Okay, questions on the sample test? Did we get a chance to look at the sample test? When are you planning to do that? On Sunday? After the test. So, any questions on the sample test? Huh? Nobody asked. They're all asking circuits questions yesterday, I think. So, the first one is liquid pressure. Do you want to see how that's done? I guess we should because it's been a while since we talked about liquid pressure. So our approach is different from the approach of the textbook and much easier. So for any liquid pressure problem, okay, we turn it into a distributed load problem, okay, by using this key equation that defines the load intensity at any point as rho G B times H, right? Or That's in the SI system when we are given the density in kilograms per cubic meter. When we're in the US customary units, we don't want to deal with masses, so instead we use gamma BH, where B is what? The width of the gate, and it's always perpendicular to the plane of the paper. Okay? And once you have identified the load intensities for different points corresponding to different elevations, okay, we can find the resultant of the distributed loads by what? Saying that the resultant is equal to the area passing to the centroid, okay, and then you can apply equations of equilibrium. So for instance here, the load intensity at this point here is 0, right? Because it's right at the surface. The load intensity at this point, let's call that W1. And W is always perpendicular to the plate, right? So this is W1. What is our W1? It's kind of hard to make it perpendicular. So what's W1? Going to be based on rho G. What is our width of the plate? Is 1, right? Times the H at point A is 0.4. Is that okay? This one here. So this is going to be 0.4 rho G will be the magnitude of W1. Okay? And how do I connect the W of 0 at the surface to the W1? It's a linear function, right? Okay? Now, on the horizontal part of the plate, what is the load intensity on the horizontal part of the plate? So at this point here, it's still W1, right? Because anywhere here, the depth is 0.4. No, it's 0.4. So this one here is also W1. Do you agree? Everywhere on the horizontal plate, it's all 0.4 meters below the surface of the water. Now, we can replace those distributed loads by their resultant. So for instance, the blue distributed load can be replaced by a single resultant. I'm going to call that R2, because I'm going to call the resultant of the red one R1, right? What's the value of R1? Oh, where did you get 0.35? It's the area of the red triangle. I think this distance here, oh, someone is asking a question on the other side. Yes, Joe. Well, they just raised their hand. 1/2 W times H. Well, what H are you talking about? It's gonna be this H here. So, it's gonna be this dimension here. I don't want to call that H, because H is 0.4, right? So to find the area of that triangle, I need this distance D. You agree, Omar? Okay. And what's that distance D? No. It's 0.4 divided by cosine 30 degrees. Yeah. No, oh, not yet. I'm finding the area first. Okay, but do you agree that it's 0.4 over cosine 30? Okay. So R1 would be 1/2 the base, which is W1, 0.4 rho G, times the base would be 0.4 over cosine 30 degrees. Okay? Jesus just sent me an email saying that you have homework 11. Okay? And yeah, you already have it, gave it to me. Now, where is that passing through? What is this distance here? This would just be D over 3, right? Because it's 1/3 of the base is the triangle. Now, we need to find R2. R2 is the area of the blue rectangular distributed load, and that's just going to be equal to 0.7 times W1. Is that okay? W1 is 0.4 rho G. Okay, once we have that R1 and R2, okay, I'm going to redraw the picture and show the resultant forces. Okay, forces acting on this are, of course, an unknown y component AY here, and an unknown x component, and a BY here. Okay, and then I can show the resultant of the distributed load. Okay, I'm going to have an R2 here, which I already know. Okay, and I'm going to have an R1 here, which I also know. Okay, so I'm going to sum moments about point A equals 0. I'm going to have a counterclockwise or positive value for R1 times. What's the perpendicular distance of R1? It's d over 3, right? So it's 0.4 over 3 cosine 30 degrees, right? That's this distance here, d over 3. Okay, and plus by times perpendicular distance of by from A is 7. Okay, and then a minus R2 times, what is the perpendicular distance? It's half of 0.7, 0.35 equals 0. And since R1 and R2 are known, that will give me by by. Some forces X, all of the other forces will be known, and that will give me AX. Some forces Y will give me AY. Okay? So the only crucial step here is how do you replace your liquid pressure by a distributed load, and the key is by using this equation for W at any depth H. Yes, you can use a note card, but you are always allowed a 4x6 cheat sheet. So are we okay, Omar? I know you were kind of worried about liquid pressure. It's really not that hard, right? When you replace the distributed load by a single force, that single force should pass through the centroid of the area, right? So this one here is passing through the centroid here, and this one here is passing through the centroid. That's why I used 0.35 here, right? And I used d over 3 here. So the centroid is used to point out where the resultant force for the distributed load passes through. Okay? Now let's look at the next. This is a problem on what? Method of sections. Okay. We are interested in forces in members, what? Members, oh, it's only one, BD. Where's BD? It's right here. Okay. And we are given that the F1 is 600 and the F2 is 300. Okay. And we're going to use method of sections. When you use method of sections, you cut through members of the truss and then isolate or look at the free body diagram of one side or the other side of the cut. And when we're trying to make a cut, okay, what are our initial objectives in terms of how to decide where to cut? Yeah, you try to cut 3 or less members, right? Now, considering that we're interested in member, what? BD, which is this guy here, right? This is what we're interested in. Okay? Can you Find me a cut that goes through BD and only cuts through 3 members. Joint what? Like this? That's kind of clever, but that's not going to work, right? Because this is really just, as you said, the FBD of the joint, right? Which will have 3 unknowns. It's three unknowns if it's not the joint. You still have 3 unknowns, and you only have 2 equations, right? Do you agree? You have to cut to 3 or less, but make sure that you have at least 2 pins in it. Because if you only have 1 pin, it's really just a free body diagram of the joint B, which has only 2 equations, right? Summation x summation y, there's no moment equation if it's just 1 joint. Is that okay, Ben? So technically, although it has 3, that's not going to work because it's really not method of sections, it's method of joints. And for method of joints, you only are allowed 2 unknowns to make that joint happy. Remember? Happy joint is one with only 2 unknowns. So I don't think we can find any cutting section that passes through BD and only cuts 3. Do you agree? It cuts through at least 4. Yes? You all agree with me? I cannot find a cutting section that cuts this without cutting 3 other bars. So one option is this, that's 4. The other option is this, that's also 4, right? The other option is this, but again, that's disqualified. It's just FBD of joint B. Okay? Even if I go here, that's still 4, and I might even need to find the reactions here. So we all agree that in order for me to pass through the pink bar here, BD, I have to cut through at least 4. Okay? We agree with that? So this is the best we could do at this point. What I know is I'm probably not going to be able to solve for BD there because I have 4 unknowns. So what do you suggest we do? Find the ones. Do you think we can find any from there? From the cut? Okay. If I sum here, I'll have 2 unknowns. These 2. If I sum here, I'll have these other 2 unknowns. I don't think we can find any of them. Do you want to see? So Victor is trying to see if we can find some of them, which is not a bad strategy if you can, but I don't think in this case we can find any of them. So here are the bars that I didn't cut. I'm looking at the right side. So in addition to this 300, do you understand what this part is? That's A and that's B, okay? So I'm exposing, what is this? FBD, that's the one I want, right? This one here is FBC, yes? This one here is FAC, this one here is FAE. I cannot solve for any of those 4. My possible equations are some forces vertical, forget that, there's 3 of them, or 2 of them. Some forces horizontal, all of them will have. Some moments about B, it only takes care of the 2, I still have 2 unknowns. Some moments here, still has, right? Another option is some moments here at about point C, I'll still have 2. So there's no way to, okay? So any suggestions on how we should approach this? Look at the other side, and with the intention of making this happy. We can try to make this happy before going to find FB, which we're trying to find FBD, which means that if we can find one of these other 3 before going here, I know I can do it. So what do you suggest we do? So my objective now is I'm going to look for either FBC, FAC, or FAE from another cut. Can you see a cut that goes through one of those three and only cutting 3 unknowns? Very good. So if we go here between, what did you say? If I get a cut here between G and D, between C and D, C and G, and E and A, right? That only cuts 3, and it cuts through one of my unknowns FAE, meaning that from that FBD of BB, I should be able to find FAE. Once I know FAE, the other section, FBD of section AA, will be happy. Right? So the first part of the plan is section BB. Okay, and let me draw everything to the right that I didn't cut. Here's my D, here's my C, here's my D, here's my A, okay, and I didn't cut this, I didn't cut that, I didn't cut through this, didn't cut through that, I didn't cut through that. I cut through GD, I cut through CD, and I cut through AE, right? So that will expose 3 unknown member forces. Oops, CD is not horizontal. CG rather. CG is going this way. Oops. Going this way, right? So that will expose 3 unknowns. What is this? This other one here would be what? Oh, where did it go away? This would be FCG. Oh, my bar disappeared. Oops, that should be blank. Okay, and I have another unknown down here, FAE. Okay, so what do I do from the FBD of section BB? I'm going to sum what? Which one of these 3? FDG, FCG, or FAE should I try to solve for? FAE. And how do I do that? Some moments about point G. Right? So point G is over here. That's where the 2 other unknowns intersect. Right? So, oops, I forgot to show my 300. Right? So some moments about point G, I will leave it out, the summation, okay? This will allow me to find what? FAE. Is that okay? Once I found FAE, this is now known, right? This is now happy. So how do I find, what am I looking for? FBD. So what do I do to find FBD? So second part of the solution would be a summation of moments about where? I already have FAE. I want to find FBD. That means I need to eliminate BC and AC. How do I do that? Some moments about point C. Because those 2 unwanted unknowns will intersect at point C. And that will allow me to find FBD. Okay, is this problem clear now? So we tried going through BD, we couldn't find anything that cuts only through 3, so what we did was, let's try to find one of the other 3 before going to that free-body diagram. Okay? But in general, your first objective in method of sections is what? Look for a cutting section that passes through only 3. If it's not possible, that's the only time that you might consider for. Okay, let's go back to the sample test. This is number 3. The diagonal numbers EH and FG are known as counters. So this might be confusing for some people. So let's look at let's just look at what it means to have a counter. Okay, so it says here the diagonal members EH, which ones are those? EH, this guy here, and FH, EH, no, and FG, this one. Those two are counters, okay, and can only act in tension. So you can imagine that EH and FG, imagine them to be ropes or cables rather than bars. You know that a rope can sustain a tensile force, but it cannot sustain a compressive force. Okay, so that's what it means to be a counter. So, right here. Okay. So they can only act in tension. So that means only one of them will be working at any given time. Because if FG is in tension, so I'm trying to move F and G away from each other, the other two pins E and H are moving towards each other. Right? So there's only two possibilities. Either I'm stretching FG, in which case EH will have no force in it, okay, or I'm stretching EH, in which case FG will have no force in it. Okay? But we don't know which one's which. Right? So how do we solve this problem? So we have one of two possibilities. The first one is the force in FG is tensile, in which case the force in EH has got to be 0, right? Generally, if EH is a bar rather than a rope, okay, imagine EH to be a bar, not a rope. If I try to stretch FG, this will be compressed, right? But since it's not able to sustain a compression, we just say it's 0 in this case if FG is tensile, right? So that's one possibility. The other possibility is what? It's the EH that is being stretched, okay, in which case, what? The FG must be 0. We don't know which one's which. Some of you may be able to visualize what's happening, but the easiest thing to do is just assume one scenario. So for instance, I'm going to assume the first, oops, what happened? It disappeared on me. I'm going to assume this. So if I assume that, I have to make sure that I get a value of FG that's tensile, and then if I get a value of tensile for FG, I'm done. Right? So I'm going to take a cutting section. What's my cutting section now? It's right here, right? Okay? How many unknowns will I have in this cutting section? How many did I cut through? 4. However, how many unknowns would I have there? 3. Why? Because my assumption is that pH is 0. Okay? So if I take a look at the free body diagram of that section, let me draw it here. So here's the top part. Okay? Then I cut through FG, right? This is E. This is F. Which one's going to be 0? EH. So this one here would be here. This one. I just choose one of them. I am not 100% sure that it's correct, but I can verify if I'm correct. If I get a positive value for FFG, FFG is really tensile, I'm correct. If I get a negative value for FFG, that means I made the wrong assumption. I will redraw the free body diagram under assumption number 2. Okay? So my forces are, this is 20 here, and then P is 40, so I have a 40 here. Okay, and then I only have 3 unknown forces here, and they are F, E, G, F, F, G, and what's this? F, F, H, right? So what do I do now? This is a happy SBD, right? So I should be able to solve for all those unknowns. Okay? So any suggestions on how I should solve? Maybe some moments about point E. This will give me F of H. Then some moments about point, what is that? F will give me F, E, G, and then some forces X or some forces Y, doesn't matter, will give me F, F, G. So how do I know whether I made the correct assumption? Okay, after I do my solution, I'll just inspect this one. If I get a positive value, if it's really P, positive or tensile, then I'm done. If I get a negative value for this, that means my assumption was wrong. Meaning, under this configuration, the FG is not under tension, it's actually under compression, which means that the FG is the one that's 0. So I'm going to repeat the whole solution. Are you okay with this here? I can find all the 3, yes? And the important thing is FSG. I find what FSG is. Okay? If I get a positive value for it, then it's tensile. My assumption is correct. If I get a negative value, it's supposed to be compressive. And I know that I'm wrong because FG cannot sustain a compressive value. So I go to the second possibility where this is the one that's 0 and EH is the one that's tensile. I repeat the process again. Okay? Let's do this one because I don't have a lot of time to look at all of them. I like this one because it combines frame problem with chapter 7 problem, finding the internal forces and bending moment in a specific point. So this problem has 2 parts. Okay, finding the reactions, and then the second part is finding internal forces. Okay, you agree that this is a frame problem, right? So what's the first step in a frame problem? What's the first step in a frame problem? No, it's not the first. Okay, so do you see any 2 force members here? How many members do you see? 4, right? The 2 horizontal bars, 1 vertical bar, and 1 inclined bar. So there's 2 force bodies here. Okay, let's label them. Call this C, B, E, F, G, and H. Okay? So which ones are 2 force members? Okay, D, G, and E, F are 2 force members. Okay? That's the first step. What's the second step? Okay, find external reactions at what kind of external supports do we have? Both of them are pins, which means that I will have two pairs of unknowns, an hx and an hy at pin x, and then a cy and a cx. Okay? So after looking at the free body diagram of the frame, doing it lazily, I'm the only one allowed to do that. Okay? What's your conclusion? It's not happy. However, what? Do we abandon this simply because it's not happy? Oh yeah, we can try and find the ones we can, right? So which ones can we find? Before we do that, maybe I will replace the distributed load by a single resultant R. What's the value of R? It's 3 meters multiplied by the magnitude, the load intensity, which is 4, is going to be 12 kilonewtons. Okay? So even though the FBD, so the first part is FBD of the frame, okay, even though it's unhappy, we should be able to solve for some of the unknowns. Which unknowns can we find? Cx by coming moments about point A equals 0, I will get minus Cx, okay, times 2 meters minus the R, which is 12, times what's the perpendicular distance? 1.5, right? Yes. This will give me equals 0. This will give me a Cx of minus, what's that? 3 over 4, it's 9. Okay. And then we can find AX, summation forces X equals 0. We'll find AX, right, minus 9 for CY equals 0, which means that AX is just 9. What's the next step? After finding FX, AX, and CX, what's the next step? You take them apart, right? Okay, I'm going to put in green the ones that you already know. We know Cx is minus 9. AX is 9. Okay. We still don't know Cy. We still don't know AY. Okay. I know that there's an R here equal to 12 kilonewtons. Okay. What other forces are acting on CDE? Okay, the resultant on CD, right? Because it's a two-force member, I know that. Oh, you want to have it compressive or tensile? What do you want? Upward? Okay, so let's do upward here. This is RCD, right? What else? Okay, the other resultant here, we're going to call that REF. I'm also going compressive. I think our FBD of CDE is now complete, right? Except the RCDs should be slightly to the right, huh? Not exactly, okay? And then the other RCD will be over here. And the other REF will be here. Okay? So what do we do? Okay, he is saying, find moments, I like that, or maybe I don't know. Right? Find moments at the intersection of these two. Is that pretty easy to find? It's 1 by 2. So it's going to be at the distance 2 here. Yes? 1 here. You agree? Or are we getting nervous here finding this? Do you all agree that they intersect here at 2 meters above point E? Because the slope of this bar is 2 over 1. So if I extend that there, it would also be 2 over 1. Okay? So he wants to do it that way. If you're getting nervous about that, finding intersection outside the body, it's okay. This is a happy free body diagram. There's 3 unknowns. I can find all 3 of them if I want. I can find some forces X to give me CD. Right? Once I have CD, I can some moments here, that will give me 0. But let's give Victor's solution a chance. I like it actually because he's not scared. You all agree that the intersection is 2 meters above. So he wants us to some moments at, so this is the second step, FBD of CDE with some moments about point O where the 2 R's, RCD and REF intersect. So we're going to have, what are our terms? I'm going to have, it's a minus 9. Okay, so it's a minus 9 times 2. Be careful, okay? You see where I'm getting this minus 9? This is actually, according to the arrow, it's a positive moment. So it's a minus. It's a positive minus 9. Okay? Are we okay with that? Positive minus 9. Times 2. And then what? The R was, what is this? 12? Is that 12? Yeah. And it's also a plus 12 times 1.5, right? Minus CY times 3 equals 0. Okay? I'm worried about this one here. Are you guys okay with this? Why it's a minus 9 times 2? It's actually a positive moment about this if you look at the arrow, right? But the force itself is minus, so I put the minus. So if you are getting nervous about that, is what you do. Once you got the CX to be minus here, you'll just say, it's actually CX is 9, but it's going to the left. Right? So when you redraw it here, you can assign a value of positive 9. Oops. You can assign a value of positive 9. I don't know, I erased something that I'm supposed to. As long as you're showing it to be to the left. In which case, what? This is still consistent with that. It's now a minus moment because it's clockwise, but the force is positive multiplied by 2. It's equivalent. Okay? Anyway, once you find CY, from here, I don't really need to find all the other forces. It really just wants me to find the internal forces at point B. And once I find CX and CY, I can cut through point B and look at the free body diagram on the left. I'll find the V, the P, and the M. Yes? That's what I'm looking for. So don't waste your time trying to find RD, RDG, and REF, and AY. It's not needed in the problem. So the next part of the problem now is FBD of the section at B. Okay? The important thing to remember is when you take a cutting section through point B, you need to make sure that you cut through the distributed load. Okay? Don't cut it over here where you have replaced the distributed load by the 12 kilonewtons. You have to cut the original one. Okay? So our free body diagram would be a tiny piece of C, this is J, right? Or B. And we will have the blue distributed load of load intensity 4, right? And then we have the Cx and the Cy. We already know Cx to be 9 to the left, and we know the Cy from here, right? And then on the right side, what would I show? Because I cut the bar at B, I'm going to have a force to the right. What do we call that? That's the axial force P, right? And we're going to have the shear force V. What's the direction of the shear force? Up or down? Should be down, right? Because a positive V should rotate that bar clockwise. And then we have a smiling M. So is the M clockwise or counterclockwise? Counterclockwise is the M. Just some forces X, that will give you your P. Some forces Y, that will give you your V, and summation of moments at point B will give you my M. And these are the internal forces and bending moments that it's looking for. Okay? Now let's continue this business on shear and bending moment diagrams. 240, 230. I've already shown you last time how to construct shear and bending moment diagrams. 15 plus 7. This is not it. It should be 8. Okay, remember this? We already successfully constructed this fairly complicated shear and bending moment diagram. Okay, now what are we trying to find here? Relations between W, V, and M. How come there's no diagram here? Okay. So if you noticed, or maybe you didn't, okay. We already know how to find shear force as a function of X by cutting at different sections of the beam, right? By applying equations of equilibrium to find V, and then find M, and then plotting the resulting equation. That's exactly what we did before, okay? But if you know the relationships between these three variables, the load intensity W, the shear force, and the bending moment, there's actually a graphical, quicker way of constructing your shear and bending moment diagrams. So how do we do that? Let's look at an example of a beam here. Okay. This is the beam. Okay. And let us say that to make this simple, I'm going to say we have a pin there and a roller there. And let's say that we have a load intensity W that in general is a function of X. Okay, so, and to make it simpler, I'm going to make my load intensity positive, going upward. So it's changing along the length of the beam as a function of X. So if I take a look at a specific location, say X here, okay, and then I take an infinitesimally small element of the beam here, which is, say, dx. Okay, and I cut 2 times, 1 to the left of that. Let me use a different color. I cut, say, 1 to the left of dx and 1 to the right. Okay, and I look at the free body diagram, so I'm going to expand that part here and look at that free body diagram. Okay, so that element of the beam is a tiny little section here. Let's use the other color. Here's the beam, okay, and the length of that beam is dx, right? Okay, and I have a load intensity W as a function of x on the left and W as a function of x on the right. So in general, this may not be exactly equal to each other, right? Okay, which means that since I cut it at two different sections, okay, one to the left of this tiny little section, in general, I'm going to have a V, right? And I'm going to have an M on the left side. What's the direction of the V on the left side? Up or down? It's going to be up, right? Okay, instead of making this infinitesimal, let's make this finite, sort of finite. Delta x, delta x. So why is it up? Because for any unknown internal force or bending moment, we assume it to be positive. And a positive V is supposed to rotate this clockwise. That's why it has to be up. In the same way, the M on the left side has to be clockwise to make it smile. Is that okay? So that's my M on the left side. Now on the right side, I will also have a V, right? But the V on the right side should be downward for it to be positive. And in general, that V on the right side is not going to be exactly the same as the V on the left side because I cut it at two different positions, right? So the right side, instead of saying it's also V, I'm going to say it's a V plus some change in V due to the fact that I'm at a different location now. Okay? Similarly, the bending moment on the right side, number one, has to make the beam smile, so it has to be counterclockwise. Number two, its value is not necessarily going to be M, right? But it's going to be M plus some additional change in M due to the fact that I'm now at a different location. Is that okay? But I know that this system should still be in equilibrium, and as such, if I look for the resultant of the distributed load, R, what is that R going to be? Approximately equal to? What? Say that again? Because I want W to be positive rather than negative. Okay, so my equations mathematically will be better. So, what is the value of R now? The value of the distributed load is equal to the area, right? What's the area of that distributed load? What's the height of that distributed load? It's W, right? The W where I am at X, and the width is delta X. Is that okay? I'm going to approximate it as a rectangle, right? And that's why, the reason why I took a small section delta X. Okay, it's not exact right now. It's not exactly a rectangle, but as I let delta X approach 0, it's going to become an exact rectangle, right? That's the whole idea behind calculus. Okay, so if I sum forces along Y now, for that tiny free body diagram, I will see a V going upward and a minus V plus delta V going downward, right? Plus what? An R, which is W delta X. Everyone okay with that? I only have three forces. V and R are positive, and V plus delta V is negative, equals 0. And this will give me an equation that what? The V's will cancel. Will give me what? Delta V is equal to W delta X, right? So that W is delta V over delta X, right? And this is only approximate. Why is this approximate? Because this area of the rectangle is not exactly a rectangle, right? So what do I do to make it exact? Well, we apply our our calculus, we take the limit as delta x approaches 0, right? Because as delta x here becomes smaller and smaller, the value of the w on the left will be approaching the value of the w on the right. So it's becoming more and more like a rectangle, so this is no longer an approximation. Okay, so as you can see, we do that, the w now becomes, what happens to the delta v over delta x as delta x approaches 0? That's really the definition of your derivative. Okay, so what this tells me is the value of the load intensity at any point is equal to the slope of the shear force. Okay, now if I some moments about point C here, okay, what would I get? The m on the left side will be clockwise, right? And then the minus v times delta x, right? The moment of the v is clockwise also. And some moments here, the v plus delta v will have no moment, and the m plus delta m will be positive, right? Plus, what do I have here? M plus delta m, and let's not forget, what else? This guy here, the r, is also the moment. What's the moment of the r? It's going to be minus, right? What's the value of r? It's w delta x, yes, multiplied by, what's the perpendicular distance? I'm summing moments here, and I'm accounting for the moment of this. So what's the perpendicular distance? Delta x over 2. Again, I'm approximating that by a rectangle, right? So this is really just approximately equal to 0, right? And the m's will cancel. Oops, I didn't mean it to cancel that way. It got erased. I was going to cancel it like mathematically like this. And if I solve for delta m, what would I get? I'm going to have two terms. The first term is v delta x. The second term will be 1/2 w delta x quantity squared. Okay, I'm going to divide everything by delta x. That's going to cancel. Plus, what do I have here? 1/2 w delta x. And that's approximate. So what do I do to make it exact? Limit as delta x approaches 0. Okay, the left side becomes dm dx, right? Must be equal to v. What happens to the last term? As delta x goes to 0. Just goes to 0, right? And the delta x is in the numerator, right? So here are our two results. Okay, these are very important results. What this tells us is the value of the load intensity is equal to the slope of the shear diagram. The value of the shear is equal to the slope of the bending moment. Let's and see from our previous examples if these two relationships are really true. Okay? Anywhere between between the left side to point B. What can you say about the value of V? The value of V is a constant. It's 150. And what did we say about the first relationship? W is the slope of V, right? What's the slope of V here? What's the slope here? 0. Do you see any distributed load? No, because W is 0. Okay. Let's look at between B and C. What's the slope of this? If you want to compute the slope, it's going to be what? Minus y2 minus y1 divided by x2 minus x1, right? So it's minus 1050 minus 150 is negative 1300 divided by 12 minus 6, which is 6, right? No, it's 1200. So minus 1200 divided by 6. So what's the value of the slope here? Minus 200. Does it agree with the W down up there? The load intensity is a downward 200, so it is a minus 200. So this is true. Obviously here on the right side, the slope again is 0. Therefore, there's no arrows, no distributed load there. Yes, it looks like it's consistent. Okay. Similarly, we try to do this, verify this graphical relationship between the two. Okay, it says here that the slope of the bending moment at any point is equal to the value of the shear force. Let's find the slope here of M. This one here is 900 over 6, right? So what's the slope? 900 divided by 6 is indeed positive 150, right? So what can you say about the slope here? Well, it's a curve, right? Right? But I know that the slope is positive and decreasing, right? And what can you say about the V? It's positive and decreasing. So in fact, okay, the highest point here, that's the vertex, actually corresponds to the x-intercept of V, right? Because at the vertex, the slope of M is equal to V, right? The slope of M is 0, and that's where it intersects. If you continue here, the slope is what? Always negative and increasing in magnitude, right? Look at the slope here and increasing in magnitude. Same thing here. What's the slope on the last range here? It's 1800 divided by 6, right? Which is probably 300. This is probably 300 here. Okay? So indeed, these relationships are true. Okay? And we can use this to graphically construct the shear diagram from the load load diagram and the bending moment diagram from the shear diagram. Now, have you seen relationships similar to this, say in physics or maybe Calc 1? You have three variables wherein what? The first derivative of the first variable with respect to time is the second variable, and then the second derivative is the third variable. Have you seen similar relationships in physics? Yeah, and kinematics, right? What are the relationships? V is equal to dx dt, right? And what? A is equal to dv dt, right? So how is this synonymous to this? So it looks like x. Well, which one's your A? So the x here is actually your independent variable. It's your time in kinematics, right? And which one is your V here? I think this V here is what? The velocity, right? And the M is the position x, and the W is the acceleration. Can you see that? This equation here is actually this. And this one equation here is actually that. Yes? So in physics, you remembered cases wherein you're given an acceleration graph and you solve the velocity from acceleration, and once you have the velocity, you solve the position. So it's very similar to that. I think the more common case in physics is you're given position, and then you look for velocity and you look for acceleration. But I think you've also done it backwards. you're given a graph of acceleration, and then you're trying to find velocity from the acceleration graph, and then from the velocity you find the position. So really here, how do we find v? Here, you can just say the change in v between any 2 points is equal to w dx, which is the area under the graph, right? Same thing here. If you want to find m, the change in m is just equal to the area under the curve of v. So let's see how that works here. So how did I know that it goes from that the change here from point A to point B is 0 for B? Because there's no area between A and B. How did I know that I needed to go from 150 to 1050? What you can do is find the area here. What's the area? Since the arrow is downward, the area is minus 200 times 6. It's minus 1200. Therefore, the change in the shear force between B and C would be equal to minus 1200. So if you started at 150, just add the minus 1200, you'll end up with minus 1250. Okay. Same thing here. How would you get the 900? Well, if you find the area here, what's the area there? It's positive because it's above the x-axis. 150 times 6, that's actually 900. So if you start from 0, just add the 900, we'll end up here. Because of this relationship here, the change in m between any 2 points is equal to the area under the V diagram. Okay, so we're going to use this graphical relationship. W is the slope of V, therefore V is the integral under the W, and M is the integral after the V. However, okay, so those of you are observant, what is the main difference between graphing shear and bending moment diagrams from graphing position, velocity, and acceleration? What is the main difference that you see? Anyone? Oh, you can have negative values for velocity. You're moving to the left, negative, right? Any other opinions? Can this be the graph of velocity? Why? It breaks right here, right? You cannot go from a velocity of minus 1050 to 300 with no time involved. Okay? It's impossible. Even if you get the most powerful car, it will take a finite amount of time to go from minus 1050 to 300. So the main difference between graphing accelerations, velocity, and position, which you did a lot of in physics and even in Calc 1, maybe even Calc 2, when you're trying to find the relationship between integrals, area under the curve, derivatives being the slope, okay? In all of those applications in calculus and physics, the functions were all continuous. So you will not see any of this vertical jump here, in which case it's allowable here, okay, but not allowable in velocity and position. Position cannot be discontinuous there, right? I cannot go from x equals 0 to x equals 100 without passing through 1, 2, 3, 4, 5, 6, 7, 9900. But here, I can go from a shear force of minus 1050 to a shear force of 300 in no time at all. Similarly, although it's not shown here, M can also jump. Bending moment can also jump, and we will see those scenarios next time. Okay, but I want you to see from here is that instead of, do you remember how we solved for all of this? How we graphed them? We cut them at different sections, and then we came up with equations, and we graphed these equations like we were in Algebra 2, graphing lines and parabolas, okay? If we know this graphical relationships between W, V, and M, we can generate the shear and bending moment diagrams graphically by computing areas under the curve and slopes. just like you did in working with velocity, acceleration, and position. With the only complication that sometimes we may have jumps. So we need to investigate when do we have a jump in shear force? When do we have a jump in bending moment? And it's just by inspection, okay, if you are observant, you should notice that the jump here is how much? Starts from 0 to 150, it jumped by 150, corresponding to the concentrated force here of 150. If you look at here, here's the other jump from 1250 to 300. Is that 300? 1050 to 300. How much is the jump? It's more. How much is it exactly? 1350. Do you see anything? 1350 in the. Here's a concentrated load of 1350. Here's another jump here. How much is that? Minus 300. Oh, there's a downward 300 there. So by inspection, you can see that what jumps in V actually correspond to concentrated forces applied on the bar. We will see that next time. Now, how do we find jumps in M? It doesn't have any jumps here, right? Anyone with a guess? What do you think can cause the M to jump? There's nothing here, right? There's no jump in M. M is continuous. I was able to complete all the graph without lifting my pen because there are no external couples applied. If I have a couple here somewhere, say I apply a couple here, that couple will create a jump, as we will see next time. But we should stop now because I'm giving a test in my next class. Bye, Joe. No shear and bending moment diagram on the test. There will be 4 problems. Bye. I'm gonna kill you now. I feel so powerful.